Howdy, and welcome to video 4.1, where we're going to talk about molecular geometry and intermolecular forces. Let's talk a little bit more in depth about covalent bonding. We know that covalent bonding results from the sharing of electrons between nonmetals. And really, a covalent bond is a region of space between two atoms that contains a shared hybridized orbital called a sigma bond. For example, when I'm thinking about a fluorine molecule, diatomic because of Honkelbrief, really we have 7 electrons belonging to each fluorine, each one having 1 electron that belongs in the middle that's being shared by the 2. This is the covalent bond. And in this particular case, we call this a sigma bond. So it's the region of space between those two nonmetals that's creating that covalent bond. There are often conditions where we have regions of space above and below, or forward and backward, of two atoms that contains shared unhybridized p orbitals called the pi bond. So in this example, I have sulfur dioxide. So the oxygens are bonded to the sulfur through these sigma bonds that are right here, in between the sulfurs and the oxygens. Above and below, we have this second bond called a pi bond. So it's really not existing between the two, it's above and below, linking them together in a different way. And one of the things we're going to be talking about is determining the geometry, the shape of the molecule. So what we have to know is what is the placement of those valence electrons within that molecule. So the geometry is determined what's called the VSEPR model. That stands for valence shell electron pair repulsion, meaning that pairs of electrons in the valence shell are going to repel one another because they have the same charge. VSEPR models allow us to visualize the structure of a molecule due to the proper placement of atoms and lone pairs of electrons bound to the central atom of a molecular compound. So we're going to use something called Lewis structures to determine that. Let's go through the rules for Lewis structures very quickly. The first step is to find the total number of valence electrons, we call the N, for the atoms according to the column in the periodic table they occupy. Also, we need to account for the charge of the atoms and the charge of the molecules. So if something has a negative charge, it has extra electrons. If it has a positive charge, it has fewer electrons. But as we know from the periodic table, group 1 are lithiums, sodiums, potassiums, which we won't talk about because we're really talking about molecular bonding. So we'll really be talking about hydrogen, has a valence of 1. Beryllium in the second column has a valence of 2. Skipping the D block over to the P block, boron, aluminum, those guys have a valence of 3. Carbon, silicon, that has a valence of 4. Nitrogen, phosphorus, arsenic, valence of 5. Oxygen's columns, a valence of 6. Our halogens are a valence of 7. And our noble gases have a valence of 8. 1, 2, 3, 4, 5, 6, 7, 8 across the periodic table. So we're going to add up the valences of all the elements in that compound, then add or subtract electrons to account for charge. The second step is to draw a skeleton structure with single bonds, what we are calling the sigma bonds. The central atom of the molecule is usually the one that's the least electronegative atom, or the atom with the highest valence. Hydrogen and halogen atoms tend to appear on the outside of the molecule and are rarely seen in the center. Our third rule is we're going to place the remaining electrons around the perimeter, the non-central atoms, to give each one access to 8 electrons, an octet. Exception to this include hydrogen, which only needs access to 2 electrons. It just needs 1 bond. Beryllium needs only 4 electrons, which is a total of 2 bonds. And boron needs only 6 electrons, so it can form 3 bonds. So everyone needs access to 8, with the exception of hydrogen, which bonds once, beryllium, which bonds twice, and boron, which bonds 3 times. What are you doing? All right. Rule 4. We're going to place the remaining electrons around the central atom to satisfy its octet, meaning its access to 8 electrons. So we're trying to give everyone 8 electrons here. If you're electron deficient, you don't have enough electrons to give everyone 8, we're going to start creating double or triple bonds by using electron pairs from those peripheral atoms. If you have extra electrons, then you're going to place them around the central atom, creating an expanded octet. So the central atom may end up with 10 or 12 electrons around it, if you have too many. So let's take a look at a few examples here. The first one is carbon tetrafluoride. So we look at our periodic table to determine how many valence electrons everyone has. The carbon has 4 valence electrons. Then there are 4 fluorines, each with 7. So the total number of electrons I have to show is 32. This is directing how my Lewis structure is going to be shaped. It's going to end up showing 32 electrons. Second step is to draw my skeleton structure. In this case, I'm going to show carbon in the middle, obviously. Fluorines, being the halogen, will always be on the outside, almost always. Now, each of these lines represents 2 electrons. So I'm showing 2, 4, 6, 8 electrons already as my sigma bonds. Sigma bonds are the ones that are holding it together. If I subtract the 8 from that 32, it gives me 24 electrons I have to show in addition to these. So the idea is you're going to place them in pairs around the outer peripheral atoms to give everyone access to 8, an octet. They already have 2, having the sigma bond already attached. So this fluorine has 2 electrons. I'm going to place 2 here. Well, let's place them in pairs. 4, 6. Now that fluorine has access to 8 electrons. It has the bonding 2 here, then unpaired electrons in that region for a total of 8. So there's 6 electrons, 7, 8, 9, 10, 11, 12. That fluorine's good. 14, 16, 18. That fluorine's good. 20, 22, 24. Good. Now I'm showing my total of 32 electrons. 8 are bonding, 24 are non-bonding. Everybody has access to 8 electrons. Again, 2, 4, 6, 8. He's good. 2, 4, 6, 8. Yes for that one. 2, 4, 6, 8. Yes. And the carbon itself, 2, 4, 6, 8. The bonding pairs count as 2 for both elements. That is a good Lewis structure. Let's take a look at the Lewis structure of the nitrate ion, NO3-. So the nitrogen has a valence of 5. There are 3 oxygens, each with a valence of 6. And because it has a negative charge, that must mean there's an extra electron added. So I have a total of 24 electrons in this Lewis structure. Second step, let's draw the skeleton. So now I'm showing 6 electrons as bonding. So I'll subtract that 6 from the 24. Now I have to place 18 electrons. Start with the perimeter, giving everyone access to 8. So there's 6, 12, 18. Now I am showing the 24 electrons. But, sure, this guy has access to 8. This oxygen has access to 8. This one has access to 8. But my nitrogen does not have access to 8. There's a problem. So, if we are electron deficient, what we're going to do is we're going to remove 2 electrons from the perimeter. Doesn't really matter which ones I'm going to use. And I'm going to add those 2 electrons as a double bond. Now, when I look at this oxygen, it has these 2, these 2, these 2, and these 2. So there's 8 electrons around this oxygen, but now there's 8 electrons around this nitrogen as well, each line representing 2 electrons. By the way, that other bond I just tossed in, that is that pi bond that I showed you a second ago. All of these other ones are sigma bonds. when we're dealing with an ion, to put the whole Lewis structure into a bracket and then indicate the charge of it right there. The completed Lewis structure also shows the charge. Let's take a look at hydrogen sulfide. Now hydrogen has a valence of 1, but we have 2 hydrogens. Sulfur has a valence of 6, so this Lewis structure will show 8 electrons. And again, there are 3 exceptions we need to be aware of, and they're at the top left of the periodic table in columns 1, 2, and the first P block. Hydrogen, when we draw a Lewis structure, is always just going to bond once. It does not need electrons out there. It will never have electrons out there. Beryllium will always bond twice. It will not have electrons outside of that. It just has 4 electrons total around it. And that other exception we mentioned is boron, which will form only 3 bonds. These are the only exceptions we're going to ever talk about, okay? They do not require an octet. My point being is when I draw my skeleton structure, I do not need to worry about giving hydrogen access to any more electrons than I'm showing already. Hydrogen is fine. So I'm showing 4 electrons in my Lewis structure already, meaning I have 4 more to place. Where should I put those? Well, sulfur is not an exception. It does need 8 electrons. So that is my Lewis structure for hydrogen sulfide. Last one I'll look at right now is Xenon Tetrafluoride. Yes, xenon can bond under weird circumstances. My electron count here, xenon being noble gas has 8 electrons. Then I have my 4 fluorines, each with 7, and that's going to give me a total of 36 electrons. Draw my skeleton, showing now 2, 4, 6, 8 electrons. Subtract those from my total, I have 28 to replace. 28 to place. So, 2, 4, 6, that fluorine's happy. 8, 10, 12, that fluorine's happy. 14, 16, 18, that's happy. 20, 22, 24. Everyone's got access to 8 electrons, but I still have 4 more electrons to place. So this is where we run into the concept of expanded octets. If you have too many electrons, you're going to place them around the central atom to create this expanded octet. So there's actually 12 electrons around that xenon. That's just what you do if you have too many electrons. If you don't have enough to give everyone 8, you do double or triple bonds. If you have too many, then you put them around the central atom. Oh, what the heck, let's do one more. Diatomic nitrogen. So 5 electrons in each nitrogen, and I've got 2 of them for a total of 10 electrons. Did my math a little bit different there, but that's all right. Skeleton structure. There's 2. There's 4, 6, 8. That nitrogen's good. 10. Clearly a problem here. I do not have enough electrons to give this nitrogen its 8. So what do? Grab my little eraser, I take 2 away, and create a double bond. Now, this nitrogen has 2, 4, 6, 8, but this nitrogen on the left has 2, 4, 6, still not good enough. Follow the same rule. Let's remove 2 electrons and create a triple bond. Now, 2, 4, 6, 8 electrons around the nitrogen on the left, 2, 4, 6, 8 electrons around the nitrogen on the right, and the total is 10 electrons. Yeah, we can have a triple bond. Now, when these Lewis structures are created, the s and p electrons that are in the valence, sometimes a d or 2, will actually hybridize to form new bonding orbitals. So they no longer existing as s orbitals or p orbitals. they become this hybrid. You guys know what a hybrid is. It's a blend of the two things. Now, sigma bonds and unshared pairs of electrons that are shown in our Lewis structures are things that get hybridized. Double or triple bonds that we have to create when we're electron deficient are not hybridized. They're just leftover p orbitals that are overlapping. So let me explain this concept of hybridization. Methane is CH4. That is the gas that comes out of your natural gas system that you use to heat your stove or your water heater. When we look at methane, there's actually 4 equal bonds around the carbon. It's bonded to 4 hydrogens equally. When I look at the electron configuration of carbon, 1s2, 2s2, 2p2, you can see that it sort of looks like this carbon really would only bond twice because it only has 2 electrons to offer up for bonding. So how do we explain 4 equal bonds? Well, the idea is that during bonding, one of these 2s electrons gets kicked up into the 2p. Now we've created 4 bonding sites. But if they're all equal, how can we say that, all right, the s electron and the 3p electrons are the same? This actually creates 4 different orbitals that are all the same. We call these sp3 hybrids. Why? Because I've hybridized an s and 3 of the p's to create 4 bonding sites. There are also situations where we create 3 different bonding orbitals by hybridizing the s and the 2p orbitals. Call those sp2s. An s and 2 p's creates 3 regions of bonding. In another situation where we only hybridize the s and the p to form 2 regions of this electron density that we would just simply call sp hybrids. So 2 regions of space represents the sp hybrid. So if I'm looking at a Lewis structure that has 2 regions of density, so I have these 2 regions of space must mean X is an sp hybrid. There are situations where there are 3 regions. Maybe I have a double bond and 2 single bonds. That would represent an sp2 hybrid because there's 3 regions of electron density. Whereas 4 regions of electron density would indicate we're dealing with a hybridization of X being in an sp3 condition. Now, it is entirely possible, rather than showing a bond, these could actually be unshared pairs. Yes, that still is a region of density right there. That is still an sp2 hybrid. Or, maybe in this case, these 2 electrons that are right here still represent a region of density. Unshared pairs are also hybridized. So that represents 4 regions of density around the X, making it an sp3 hybrid. Determining the hybridization of the central atom is actually going to be very important when we get onto our next discussion, and it's very simple. So when we look at these particular skeleton structures, we can determine the hybridization of X just by counting how many things are sticking out of that X. Things, again, sigma bonds and unshared pairs. We ignore that pi bond, the double or triple bond. So, in this particular condition, in the upper left here, I have 1, 2, 3 regions of density. This X is an sp2 hybrid. In this example to the right, there are 1, 2, 3, 4 regions of density, meaning the S and 3 of the P's must have been hybridized. In this X, I have this unshared pair and this triple bond, counting as one thing. This just represents an sp hybrid. Down on the bottom here, I've got a region here, a region here, and a region here. That's 3 things, meaning an S and 2 P's, for a total of 3, sp2 hybrid. This X only has 2 things sticking out of it, an sp hybrid. The remaining X has 3 bonds, sigma bonds, and an unshared pair. This represents an sp3 hybridization. On the top left here, 1, 2, 3, 4 regions, sp3 hybridization for that X. This X, 1, 2, 3. That represents an sp2 hybrid. How about this X down here? That looks like an expanded octet. 1, 2, 3, 4, 5. How is it possible to have a 5? Well, an S and 3 P's would represent 4, but we know there's only 3 p orbitals. So what must be happening here if I have 5 regions? I must have hybridized my S, all 3 of P's, and where would we go next? You guessed it, we're going to hybridize a D. So 5 regions of space occupied by electrons would be an sp3d hybrid, and this final one represents 6 regions of density, showing an sp3d2 hybridization. And that's as far as we ever get because it just gets too darn crowded around that central atom. So looking at this visual, you can see that my red central atom is bonded to 2 separate things. This represents, of course, an sp hybridization. In this particular case, there are 3 things bonded to our central atom. This would be an sp2 hybrid. When we have a situation where there are 4 regions of density, you'll notice that now it's become 3-dimensional. We do live in a 3-dimensional world. So the drawing, when we put it on paper, may look flat, but in reality the molecule is 3-dimensional. This shape, by the way, is called a tetrahedron. Cats, stop that. So this represents our base shape for an sp3 hybridization. When we go past that octet, we end up with 5 regions of electron density. This is called a trigonal bipyramid. We'll talk about that in a bit. But this represents our sp3d hybridization. And the base shape, when we have our 6 regions of electron density, our sp3d2, is actually a shape called octahedral. And that is our base shape for that. Of course, once we have these regions of space from our Lewis structure, and we understand the VSEPR theory, the valence shell electron pair repulsion theory, tells us that those electron pairs are going to push each other away as far as possible, we end up with this whole idea of a 3-dimensional space, and we can use that to determine the geometry of the molecule, the shape of the molecule. And that's pretty much the VSEPR theory. Thanks for stopping by, and I'll see you later.